Introduction. Welcome to a mathematical journey through one of the most beautiful and profound discoveries in modern science, the logistic map. What you're about to witness is the famous bifurcation diagram, a visual representation of how a deceptively simple equation can generate infinite complexity. The equation is xt plus 1 equals or xt, 1 xt. With just three mathematical operations, multiplication, subtraction, and another multiplication. This formula creates patterns ranging from perfect stability to complete chaos. The stable region, r equals 2.5 to 3.0. We begin our journey at r equals 2.5. At this point, the system behaves in the simplest possible way. It converges to a single stable value, regardless of where it starts. This is called a fixed point attractor, like a marble settling at the bottom of a bowl. Every iteration brings the system closer to this equilibrium. Mathematically, we say the system has a single stable fixed point. There's no oscillation, no variation, just pure, predictable stability. This is the domain of classical physics, where cause and effect follow simple, deterministic rules. As r increases from 2.5 toward 3.0, the fixed point gradually changes, but the behavior remains fundamentally the same, one stable value. However, as we approach r equals 3.0, something remarkable begins to stir. The system is preparing for a dramatic transformation. The first bifurcation, r equals 3.0. At r equals 3.0, the system undergoes its first bifurcation. This is a critical threshold where the stable fixed point loses its stability and gives birth to two new stable points. The system now oscillates between two distinct values, alternating between them with each iteration. This is called a period 2 cycle or a 2 cycle. Imagine a pendulum that doesn't just swing to one side, but toggles between two positions forever. This doubling of possibilities is the beginning of the period doubling route to chaos, a universal phenomenon found in systems ranging from population dynamics to electrical circuits. The blue points on the bifurcation diagram represent every visited state. They accumulate over time, revealing the structure of the system's attractor. Watch how the single branch splits into two, like a tree growing its first major fork. Period doubling accelerates, r equals 3.0 to 3.569. Beyond r equals 3.0, the system continues its journey through increasingly complex cycles. At r is almost equal to 3.449, the 2-cycle doubles to a 4-cycle. The system now visits 4 distinct values before repeating. The cycle doubles again at r is almost equal to 3.544 to an 8-cycle. This period doubling cascade accelerates dramatically. The intervals between doublings shrink exponentially. This is governed by the Feigenbaum constant, a universal number, approximately 4.669, that appears in chaotic systems across physics, biology, and economics. By r is almost equal to 3.569, the period has doubled infinitely many times. The system has reached the edge of chaos. This is the accumulation point where the periodic orbits become dense and the system transitions from order to chaos. Notice how the bifurcation diagram becomes increasingly complex, more branches, more detail, more structure. What began as a simple line has transformed into an intricate web of possibilities. The chaotic regime, r greater than 3.569. Beyond r is almost equal to 3.569, the system enters the chaotic regime. The blue points spread across nearly the entire range between 0 and 1. The system no longer repeats itself, it becomes aperiodic, meaning it never returns to exactly the same state. This is deterministic chaos. The word chaos here doesn't mean randomness in the sense of chance or probability. It means that the system is entirely deterministic, governed by the simple equation, yet its behavior is effectively unpredictable over long timescales. The reason for this unpredictability is sensitivity to initial conditions, famously known as the butterfly effect. An infinitesimally small difference in starting value will, after enough iterations, lead to completely different outcomes. This is why weather prediction is so difficult. Tiny uncertainties amplify dramatically. Look at the time series below. The blue line represents the sequence of values for the current r. As r increases, notice how the orderly oscillations transform into irregular, seemingly random fluctuations. The red dot marks the current iteration, following the trajectory in real time. Windows of order, the islands in chaos. One of the most fascinating aspects of the logistic map is the presence of stable windows within the chaotic region. At certain values of R, the system temporarily returns to periodic behavior before becoming chaotic again. The largest of these is the period 3 window, which begins at R equals 1 plus square root 8 is almost equal to 3.828. Inside this window, the system stabilizes to a 3 cycle, then undergoes its own period doubling cascade back into chaos. This self-similarity patterns repeating at different scales is characteristic of complex systems. These islands of order within chaos demonstrate that even in the most unpredictable systems, pockets of stability can emerge. It's a powerful metaphor for nature itself. Chaos and order coexisting in delicate balance. Look closely at the gaps in the bifurcation diagram, those are the windows of order. The system appears to take a breath before plunging back into chaos. This interplay between stability and instability is what makes the logistic map so endlessly fascinating. Understanding the time series. Let's examine the time series graph more carefully. The lower panel shows the sequence x, x2, for the current value of R. When R is small, the sequence quickly converges to a constant value. You can see it flatlining after a few iterations. In the 2-cycle region, the sequence alternates between two values like a heartbeat, regular and rhythmic. As we enter the 4-cycle and 8-cycle regions, the rhythm becomes more complex, like a drum pattern with increasing polyrhythms. Finally, in the chaotic regime, the sequence appears random, no discernible pattern, no repeated values, no regularity. But remember, this is not randomness. Every point is precisely determined by the equation. If you know the starting value, you can compute every future value exactly. This paradox, determinism without predictability, is the essence of chaos theory. It challenges our intuition about cause and effect and reveals the profound complexity hidden within simple rules. The deeper mathematical significance. The logistic map is more than just a mathematical curiosity. It's a fundamental model that appears across numerous fields. In population biology, it models population growth with limited resources. In economics, it describes market dynamics in feedback loops. In physics, similar equations govern fluid turbulence, electrical circuits, and laser dynamics. In meteorology, the logistic map's principles explain why long-term weather forecasting is fundamentally impossible. In neuroscience, similar dynamics occur in neural networks. The period doubling route to chaos that we've observed is universal. It appears in virtually any system with a nonlinear feedback loop. This universality, captured by Feigenbaum's constant, suggests that chaos is not a rare anomaly but a fundamental feature of complex systems throughout nature. What makes the logistic map so beautiful is that it demonstrates how a simple deterministic equation can generate behavior that is indistinguishable from randomness. It's a powerful reminder that complexity can emerge from simplicity. That order and chaos are not opposites but part of a continuous spectrum. Conclusion. This journey through the logistic map has taken us from perfect stability to complete chaos, from mathematical simplicity to infinite complexity. What began as a humble equation has revealed a universe of possibility. The bifurcation diagram before you is not just a mathematical graph, it's a visualization of one of nature's fundamental principles. That simple rules can generate complex behavior, and that within chaos, there is hidden order. If you enjoyed this visual exploration, please like, subscribe, and share this video with fellow math enthusiasts. Follow for more visual mathematics, where we make the invisible visible and the complex understandable. Thank you for watching, and remember, in chaos, there is beauty.